Okay, so it's my pleasure to introduce today's speaker, Daniel Lester, who is an associate professor at RMIT University in Melbourne, Australia. He has a background from chemical engineering, with a PhD from the University of Melbourne in 2003. And he has been a postdoc and research scientist at the CSIRO before joining RMIT University in 2014. So in his research, he uses analytical and computational methods to investigate fundamental and applied research questions related to various topics, including but not limited to fluid flow and mixing. And I think particularly relevant to us here at Collab is his important role in the discovery that mixing dynamics in 3D porous media flows are chaotic, leading to a paradigm shift in the field. So I'm looking forward to hearing the latest developments in this topic, and his talk is entitled Fluid Mixing in Porous Media Flows of Arbitrary Complexity. So the floor is yours.
Thank you, Gaute. I've just got one small issue here. I've got a message from, there we go. I've just removed it now. I just had a message from Zoom. Okay, look, welcome everyone, and look, I'm terribly sorry about the calendar mix-up. I'll sort of launch straight into things here. Yeah, so today I'm going to talk about fluid mixing in porous media, and this idea of characterizing and understanding and quantifying mixing of flows of arbitrary complexity. So on the right here, we have an image of a series of fluorescent tracer particles that are being flowed over a static bead pack of packed beads with an index matched fluid. And in the images as they go from left to right, we're just looking at the evolution of that dye blob as it unfolds with time. And we can see for this, which is a very simplified picture of porous media flow, but even for this very simple packed bead experiment, we can see we get very complex flow structures. We're getting these filamentous structures that have been developed as the fluid weaves its way through the dye pack. And I guess the question is how do we develop tools and techniques to understand this complexity, understand what is the fluid mixing process, and develop tools and techniques to characterize that. And today's talk, we're going to talk about how do we handle flows that are very complex like this, more complex flows again that can be unsteady in time and so on, and then through the whole spectrum to very simple flows, and can we develop a framework to really characterize and understand mixing across this broad range of flow complexity. I'd just like to acknowledge collaborators who I've worked with on this topic over the years: Marco Dents at CSIC in Spain, Tanguy Leborn at University of Rennes and CNRS in France, Sylvia Lafroy in CNRS, Alexandra Vallée who was with Norway, Joris Heyman at Rennes, and I guess my original collaborators in this space, Guy Metcalf at University and Swinburne University in Australia, and Mike Tefry, and also Aditya Bandabay in India. So the outline today, I'm going to talk about a bit of background information, background motivation for the talk. I'm going to look at some examples of complex flows, and we'll also look at some simple flows, and then the challenges and considerations when we need to understand and quantify mixing in those flows. We're going to look at a classification of porous media flows from simple to complex, and then from that develop a general framework for solute mixing. We're then going to apply that framework to steady flows and then unsteady flows before summarizing. So I guess the background is, there's porous media flows can be very, very complex. One application is poro-elastic flows in the brain. It's starting to become well understood that cerebrospinal fluid in the brain is a major driver for the clearance of waste, and that is linked with understanding diseases such as Parkinson's and Alzheimer's, so on. And what drives that poro-elastic flow of cerebral spinal fluid is pressure oscillations during REM sleep. So when we go into a deep sleep mode, the pressure fluctuations change, and that changes the transport characteristics, and that improves this critical clearance of wastes, which is absolutely critical for brain function. It's not well understood, but you know, there's a lot of mechanics and transport, and obviously you can appreciate these are very difficult systems to characterize. But it's becoming better understood that the poro-elastic mechanics and the mixing and transport problems in the brain are key to this. So this linking between deformation and flow, mixing and transport is critical to understanding a lot of these health-related impacts. The motivation is that in the past decade, especially, there's been huge advances in the experimental front and being able to pull out an explosion of data with unprecedented resolution of flow at the Porous and Darcy scales, and so we can look at things like CT scanning of flows evolving and mixing in real time. And hand in hand with that, we have very advanced computational methods now that can resolve phenomena at the pore scale. And so the question is, how do we use this data? How can we use this explosion of data from these sources to predict and understand solute transport and mixing? And as I said in the introduction, these flows at the Porous and Darcy scales can range from very simple idealized flows, such as a steady two-dimensional flow, which we would consider to be regular or non-chaotic, through to more complex flows, unsteady flows, three-dimensional flows, flows that are naturally chaotic. And there's a broad range of transport phenomena that arise between those two bounds. And what we would really want is a framework to capture that. When we talk about complexity, we're talking about the flow topology, or what we would call the Lagrangian kinematics. So the question of where do tracer particles go in the flow? What is the structure of this entanglement of tracer particles? If we talk about streamlines in steady flows, what's the flow topology? And this idea of understanding things in the Lagrangian frame. So we look very much in the Lagrangian viewpoint of where particles go, and the kinematics is how those streamlines or path lines are organized with each other. If we talk about simple flows, well, what we're really saying is that there are constraints on these large Lagrangian kinematics. They are constrained heavily in a certain way, and that then plays out when we start thinking about processes such as solute transport and reaction and so on. What we're aiming to do today is develop a framework to classify, analyze, and quantify solute transport across these diverse flows that honors these kinematic constraints when they're present, but also has the flexibility to house kinematic complexity when it's present. We have some images here on the right. One is of a die trace of a simple two-dimensional flow moving through a bead pack. And you can see in that case the flow structure is well organized and relatively simple. And below that we have an image of streamlines from a computational simulation. And here we can see that those streamlines are very complex and interweaving with each other, and we need this framework to capture those two extremes. We also need to consider that, of course, a lot of these systems are stochastic, and how do we properly capture that stochastic nature of the problem? But also, sometimes the flows due to those constraints are also going to be coherent. So how do we have a framework that's flexible enough to capture that? Let's look at some motivating examples. So for complex flows, one of the things that we've known for some time now is that this simple example we looked at on the title slide of steady pore scale flow, they are inherently complex flows, and this was something that wasn't appreciated for a while. Essentially, if we talk about pore scale flow, it's a steady three-dimensional Stokes flow. So from a fluid mechanics perspective, it's quite simple. But there is complex topology at the pore scale. If we're talking about a bead pack or a network of pores, the fluid elements are continually being stretched and folded as they move through the joins in that topologically complex space. So that leads to exponential stretching of fluid elements as they move through. And there's a strong link between that process and the grain structure itself. So we can talk about the topological complexity, i.e. the number of contacts per unit volume, for example, in a bead pack. That's a measure of the topological complexity, and we can then link that back to the amount of stretching and folding of fluid elements. Now, stretching and folding of fluid elements, if it's constructed in the right sorts of way, will lead to exponential growth of material elements. So we get very strong stretching, very strong increases of material interfaces. With a small amount of diffusion, that then leads to very efficient mixing. So this topological complexity leads directly to very rapid mixing, very complex mixing dynamics. We can see on the bottom here, we have a bead pack with a series of reconstructed die traces move through there. This is an experimental reconstruction of a three-dimensional steady experiment. And we can see that as the fluorescent dye moves through and we take laser cuts through that bead pack at various instances downstream, that plume is being stretched and folded in the manner that we would expect for something that is chaotic. So we definitely have strong experimental evidence of this. So for very simple flows, if we have three spatial dimensions, pore scale flow tends to be inherently complex. And so that's the simplest possible example of complex flow at the pore scale. We can also consider unsteady pore scale flow. And this is an experiment developed at the University of Rennes by my collaborator Joris Heyman and Tanguy Leborn. And here we use the same bead pack that we looked at in the previous slide, and we injected a plume of fluorescent dye into the packs, into the bead pack. So this was a pointwise injection, and this pointwise injection was pushed into the bead pack for some amount of time, and a steady plume was developed, and then the plume was pulled back and withdrawn. And the movie here on the top right is essentially, it's a bit hard to see here. The image here on the top left is the experiment itself. There's a vertical column with packed beads here with index match fluid, so you can't actually see the beads. That it all appears to be perfectly clear. And we place a laser sheet through the top plane near the injection point of the experiment, and then a dye plume is injected into the top of the bead pack. That plume is allowed to develop and become steady, and then the flow is reversed and that dye is pulled back out. Now, the movie here on the top right is the image of that dye plume as it evolves with time. So at early times, we're seeing this elliptical region of which is essentially the dye itself. Obviously, there's no other structure there because this is right near the injection point whilst the flow is going into the bead pack, so from top to bottom. But when we reverse the flow, we'll see that the filaments of the dye are coming back out, and we get some complex behavior upon withdrawal of the dye from the experiment. So you can see that now we're getting stretching and folding of our dye plume into a complicated shape. It's not a simple dispersion pattern. There's very strong anisotropy in the mixing dynamics there, and that's well understood now to be due to the fact that there is an interplay there between a reversible flow, but a small but irreversible diffusion process due to the molecular diffusivity of the dye, which is very small, and that gives rise to these filamentary patterns. And those filamentary patterns are essentially the signatures of the stretching and folding process that we saw in the previous slide for the steady flow. So this push-pull flow gives us very complex solute distributions, even though the net fluid deformation at that imaging plane is zero. So by pumping the fluid in and withdrawing it out, the net fluid deformation is zero. We're seeing the signature of irreversible diffusion interplaying with that process. The dye plumes, as we see, are highly heterogeneous, and we see very strongly anisotropic dispersion. And this is what we would call the diffusive signature of that pore scale flow. So we want to be able to understand and characterize mixing at the pore scale. And we believe that this technique allows us to do that, even if we don't have optically clear porous materials. We can also look at steady Darcy flow. So now zooming up to the Darcy scale. If we have anisotropic porous media, we find that experiments done by Olaf Sirka and co-workers have found very efficient mixing in anisotropic porous media through the braiding of streamlines and helical flows by constructing the anisotropy in certain ways. There's an experiment here, very nice experiment done where there's been layered beads, diagonal layers of large and small beads, and that distribution of beads gives rise to a helical flow pattern that gives you strong mixing as it pumps through. And both computational and experimental studies have established that gives you chaotic type flows under steady Darcy flow. So even at the Darcy scale, flows that were traditionally considered not to be strong mixing flows can indeed be in the presence of anisotropy. We can also look at unsteady Darcy flows. So when we introduce a time component to Darcy flow in 2D, and we start to see a whole range of various phenomena. The left set of images, so the images here on the top right are a mixing pattern. We have a number of injection and extraction wells in a 2D Healy Shore cell. The light colored regions here is a light sensitive, a chemical reaction that produces light. And so we see reactions between the two chemical species occurring at the interface, and that's what the light is essentially indicating as where the interface between the two fluids are. There's 3 injection points. They're probably most clearly here shown in the bottom right here, sorry, of the screen. And the fluids are simply pumped and extracted through these ports. The bottom control set of experiments is a steady flow where 2 of the ports are extracting fluid and the central port here is injecting fluid. And so we're simply seeing the evolution of the interface between those 2 reactive fluids taking place. So the bottom control experiment here is a steady flow. In the top case, however, we're using the same ports, the same chemicals, etc., except there's some transient pumping going on, and that transient pumping essentially induces much larger growth of these interfaces. So it's mixing at some level. And we can see that the introduction of transient pumping in unsteady Darcy flow gives us stronger mixing. So certainly there is scope to engineer Darcy flows to get complex transport dynamics. We've also studied this problem in the context of a tidally driven flow. We have a simple flow simulation here where we have a tidal boundary on the left-hand side of the domain, a fixed regional gradient of flow on the right-hand side of the domain, and the interior is a heterogeneous medium that is also compressible. And under that oscillatory tidal boundary, we see that we get waves of the colors here denote vorticity, where red is positive vorticity and blue is negative vorticity. So we get these attenuating waves of vorticity moving through the system as the system proceeds, and there's also a net flow from right to left due to the regional gradient. What that gives rise to is complex mixing patterns here. So the next set of figures along here essentially plot the residence time of particles in the system. So we introduce particles on that right-hand boundary. They're vectored from right to left, and the colors here denote the residence time in the system. Now, what we find is that these red regions here, the figures increase the same system, but we're just increasing the heterogeneity of the system. We find that we get all sorts of different structures inside the flow. We get chaotic regions, non-chaotic regions, boundaries between the two, a whole lot of complex phenomena. And you can see that the red regions here are essentially correspond to the non-mixing regular regions in the flow, and they trap particles for a very long time. So the red colors denote long residence times in the system. So we also believe that in natural systems, transiently forced Darcy flows give us complex mixing and flow dynamics. And really the only way to understand these systems is by looking in the Lagrangian frame of where do particles go, what is the fate of particles, how complex is their intermingling. What we find is for these systems, we can look at altering the compressibility of the medium, and that's an important parameter. And when we do change the compressibility of the medium, we see a bifurcation from at low values of the compressibility, we get oscillatory flow due to the tidal boundary, but particles are just moving from right to left through the domain and oscillating on fairly close to fixed streamlines. As we increase the compressibility of the domain, we start to find fixed points in the flow, and technically they are periodic points in time. So over each flow period, our particles return to the same point, and we get these trapped regions in the middle. So this would be an elliptic type point, if for those who are familiar with Hamiltonian chaos, and a hyperbolic point here. And then as we increase the compressibility of the system further, this closed region here, so we're seeing a topological change from straight or streamlines that are moving through the system to trapped regions. That trapped region becomes larger, and then with increasing compressibility again, this hyperbolic point then creates a chaotic region around. So we're seeing strong mixing around this trapped isolated layer region here. So this trapped island would correspond to one of the red regions where material is trapped for a very long time. And around it, we're seeing very strong mixing and exponential stretching again of material elements, and then the normal background flow. So the main point here is just by playing around with the compressibility of the system, we're moving from quite classical porous media type behavior into very different transport dynamics that are very complex and not ones that are conventionally encountered in porous media flow. The question we're really asking today is how do we handle those sorts of situations? How do we understand and quantify mixing in those systems? So really, to summarize, the challenges and considerations are as follows. So some of the challenges or the phenomena that we've talked about is, first of all, we need to have a framework that accounts for chaotic mixing. I've touched on that briefly, but really, what does it mean? Chaotic mixing is essentially the idea that if you think about the advection of equation, so it's just the identity of what a velocity is, this system where we have the particle location as a function of time for a tracer particle just moves with the velocity. The velocity may be steady or unsteady. It may be two-dimensional or three-dimensional. This is essentially a set of ordinary differential equations. These are coupled ordinary differential equations, and they're nonlinear because the velocity field is nonlinear. And because of that, you have enough degrees of freedom in the system to admit chaotic dynamics. What does chaotic dynamics look like when we talk about the deformation of fluid elements and so on? Well, essentially, first of all, we understand that that's going to lead to exponential stretching of fluid elements with time. So there'll be growth of elements at an exponential rate. And of course, that's going to very rapidly accelerate mixing because interfaces are going to be stretched very quickly. And that comes about simply through the stretching and folding processes of material elements. So if we have slow, gentle Stokesian type flows or Darcy flows, low Reynolds number flows, but we are stretching and folding material elements as shown as this schematic here. We can imagine our blue and black material element is continually stretched and folded. We find that the length of the material elements grows exponentially in time, and likewise the width of the material elements is shrinking exponentially in time. So it's not hard to imagine that an arbitrarily small amount of diffusion will give you rapid mixing in these systems. And that's exactly what we see in these experimental images of watching these difilaments moving through the bead pack, is we're seeing strong evidence of the stretching and folding of these material elements, and we can measure this exponential growth. That exponent is known as the Lyapunov exponent. And I guess the take-home message for today is, given all of these flows, given multiple dimensions, the possibility of flows that are unsteady, chaotic dynamics is really the norm in random pore and Darcy scale flow. And the only thing that's really stopping it is these constraints on the Lagrangian kinematics. So when the constraints are present, that can reduce prohibit chaotic dynamics. But in the absence of those, because our system's random, we're generally going to have these ingredients for chaotic mixing and accelerated reaction and dispersion dynamics being present. The other consideration we need to look at, and this is strongly related with chaotic dynamics, is the braiding of streamlines. This, as I guess, is a simple diagnostic that we can use to understand whether these dynamics are present. And for all steady and unsteady flows, these chaotic trajectories that we were talking about, if we're looking in the space of trajectories, they manifest as streamlines and path lines that braid with each other. So we're talking about literally the motion of streamlines or path lines moving over each other in the same way that you might think about braiding of hair. This braiding, and if these streamlines braid non-trivially, what I mean by that is in a way that they become entangled to a certain degree. And again, the randomness of porous media systems means that braiding is typically always non-trivial. Then those fluids must be stretched exponentially. There's no way for that braiding to occur and not have exponential stretching of fluid elements. The easiest way to visualize this is on the schematic on the right here. If we look at the colored bars, or sorry, the black bars that are numbered 1, 2, 3, 4, you can see, sorry, 1, 2, 3. You can see that they undergo a braiding motion as we move from top to bottom. And if we consider a material element that's wrapped around, say, 2 of those bars, that material element has to stretch exponentially in time to accommodate the topological complexity of those bars braiding with each other. So if streamlines are making this motion, or path lines in the right frame are making this motion, then underlying that must be exponential stretching of fluid elements and therefore chaos. And in fact, there's some very nice theory done by Jean-Luc Thefaux from the United States on determining the braiding motions and then estimating the Lyapunov exponent from that. When you start looking in the literature, there's a lot of evidence of braiding of streamlines in many Poro and Darcy scale flows. So if we look at Pore scale flow, anisotropic Darcy flow that we already talked about, and other studies, there's really a lot of evidence of braiding of streamlines, but I don't think this connection is well appreciated. That all of these flows to me would be chaotic at some level. The other thing that is really important when we start talking about Darcy flow is helicity. So helicity is a measure for steady flows. It's not such a useful metric for unsteady flows, but certainly for steady flows, it's a measure of the complexity of the flow topology. Essentially, the helicity is defined as the dot product between the velocity and the vorticity. And if the helicity is 0 everywhere, for a steady flow, then that flow is non-chaotic. So it's a really useful diagnostic for looking at systems that are chaotic or non-chaotic and classifying them as such. And I guess the most important thing is for Darcy flows is that all steady 2D flows are helicity free because of the topological constraints. Your vorticity must be orthogonal to velocity. But there are also some steady 3D flows, such as isotropic Darcy flow, that are helicity free everywhere. And that's just a vector identity that comes from the isotropic Darcy equation. So once you have isotropic Darcy flow, even if it's 3D, you have this constraint that the helicity is 0, and therefore the system is non-chaotic. What we've found from looking at this problem in more detail is that these helicity-free flows actually emit a pair of 2-dimensional stream functions. So you can imagine you have a 3-dimensional flow as shown here on the bottom right. That's comprised of 2 families of stream functions, and or stream surfaces, should I say. And the intersection of those stream surfaces shown in blue and red here give you a green streamline, and they organize the flow in the same way that stream functions do for, say, a 2-dimensional flow. What that means is the existence of these stream functions, which comes from the 0 helicity property of Darcy flow, that constrains how the flow can behave and constrains these Lagrangian kinematics that we talked about. So this prohibits braiding that we're talking about on the previous slide. It prohibits transverse macro-dispersion and also prohibits Lagrangian chaos. So an understanding and an appreciation of these dynamics and these constraints that come about for some model Darcy flows is really useful. In contrast, on the top right here, we are looking at some of the braiding of or knottedness of streamlines for anisotropic Darcy flow, where these constraints don't apply, and certainly we see much richer behavior. We also need to think about singular and tensorial mixing. So the advection dispersion equation, which is really the go-to for understanding mixing and dispersion, is singular in that the limit of vanishing dispersivity is not quite the same as zero dispersivity itself. So if we think about the scalar dissipation rate, so the rate of dissipation of the variance of a scalar field, as the dispersivity of the system goes to zero, the scalar dissipation rate for a non-chaotic flow goes to zero as well. So we have a non-singular limit there for non-chaotic systems. For chaotic systems, though, we have a singular behavior, and so as the rate of dispersivity goes smoothly to zero, that scalar dissipation rate stays finite. And so this is a very important difference between solute mixing and dispersion. The presence of chaos fundamentally alters solute mixing. So very often people think that in the limit of small diffusivity, these differences don't matter. They matter a lot because of this difference in the character. So it's very important that we can classify these flows into chaotic and non-chaotic and develop an appropriate metric. The other thing is, if we talk about solute mixing and transport, this is really a tensorial measure. We have longitudinal mixing and we have transverse mixing, and it's probably best described by the figure down in the bottom right here. If we consider a solute line source, so the green line source in a flow that's moving from left to right, shown by the velocity arrow there, we could imagine that if that line is continually injected, we develop a two-dimensional sheet that this line source generates, and over time that will form the two-dimensional blue sheet shown, and a cross-section is shown as the darker blue line. If we talk about transverse mixing, now we're talking about this sheet folding in on itself and the mixing that occurs transverse to the mean velocity direction. So we're talking about how does the sheet crumple and encounter itself, and with diffusion mix with itself in the transverse direction. Alternatively, if our green line source is pulsed in time, then we could imagine that that would evolve into the red line shown at some point in time, where it's also stretched in the longitudinal direction, and it's still residing within our two-dimensional sheet, but now it can fold within itself in the longitudinal direction, and we can start thinking about longitudinal mixing. So these are two quite different mixing mechanisms, and they can have very different dynamics depending on the nature of the flow. So really, when we talk about solute mixing and transport, we're talking about something that's tensorial. It has some coordinate axes with respect to the mean flow, and therefore we need to extract those distinct components. So in this case, the Lagrangian kinematics, if we want to characterize those, we can't characterize that by a single scalar. We need a more sophisticated tensorial measure for that to understand mixing. Okay, so these are some of the considerations that we need for our framework. What's probably useful here is to now classify these porous media flows so we can look at the various types of behavior and then develop our framework accordingly. So we can draw up a bit of a table. Here we have on the left-hand side, we can think about the dimensionality of the flows, so whether they exist in 2D or 3D, whether they're steady or unsteady, and I've ranked these essentially from increasing kinematic complexity at the bottom and going up to, I guess, more simple flows at the top, or conversely, we could think about increasing kinematic constraints. We can see that the steady flows in 2D can't be helical, and 3D isotropic Darcy flow is also non-helical, as we discussed, but 3D anisotropic Darcy flow can be helical. The potential for these flows to be chaotic is exactly the same as whether they have helicity or not, so that's simple there. And then for the unsteady flows, whether they're 2D or 3D, at the pore or the Darcy flow, they can both be chaotic, as we've seen. So the question is given this classification, how to properly quantify the Lagrangian kinematics of these diverse flows. So the general framework we want to approach for solute mixing is as follows. If we think about solute mixing and dispersion, it really comes from the interplay of stirring and diffusion. Stirring is quantified by fluid deformation. So we've looked at stretching of fluid elements, shearing of fluid elements, folding of fluid elements. How much is the fluid deformed over time? Diffusion is a process that's occurring over time throughout in the background. So if we think about mixing, it's the deformation history that governs mixing rather than the total deformation at a point in time, because of that continual diffusion process throughout. So if we want to quantify mixing and dispersion in our system, we really want to look at the deformation history and apply diffusion in a correct manner. Once characterized, deformation can be used to predict mixing, and there are lamellar mixing theories for steady 2D flows. There's other theories for 3D flows, steady and unsteady, that are being developed. But the big challenge is to characterize fluid deformation. Diffusion obviously is fairly simple to characterize. We need just some diffusion coefficients and so on, but it's deformation that's more complex. And really, we want to develop a model that quantifies the concentration PDF and ultimately can facilitate models that have subgrid mixing resolution in numerical studies and so on. So we certainly have the tools and techniques for simple flows such as steady 2D flows and so on, but what we really want is a general framework for fluid deformation across this range of complexity. The simplest way and the most natural way to do that is via the deformation gradient tensor, generally denoted F, and it really just encodes a transform from Eulerian to Lagrangian coordinates. So it's a linear transform. If we think about a differential element, dx in the Lagrangian form, in the Lagrangian frame, so our initial coordinates, then at current time, that material infinitesimal vector has been transformed to small dx, just through the dot product of the deformation tensor. So pictorially, we can imagine about having a small round blob of material at time equals 0. At some later time, it's been translated to a new location and it's been stretched and compressed and possibly rotated into this elliptical type shape as shown. The deformation tensor essentially captures that transformation. It doesn't capture the new location that's inherent in the Lagrangian coordinate frame, but it does capture these first order deformations, so stretching, rotation, and shear. Very importantly, though, it doesn't capture things like folding and twisting and so on. So it certainly is not capturing all of the deformation that's happening. It's just the first order ones, but that's the most important when understanding mixing and so on. One that still needs to take into account unfolding when developing these models. The deformation tensor F is the object that we want to capture to understand fluid deformation and then put into our models of mixing. And the evolution equation for the deformation tensor is just given by the velocity gradient. So the deformation tensor df dt is the dot product of the velocity gradient, or the transpose of the velocity gradient, with the deformation tensor itself. At time equals 0, the deformation tensor is just the identity matrix. There's no deformation, and then that will evolve from there. And the nice thing is the deformation tensor, it's a tensor. So it captures our ideas of both longitudinal and transverse deformation. We can think about our material elements being injected into the flow and being stretched in the longitudinal and transverse directions, and it will capture those differences in orientation and so on. So it has the right sort of properties for what we need. And we can also see that deformation history directly controls mixing. If we think about in 2 dimensions or 3 dimensions, a Gaussian solute blob, it has initial position x0 and initial covariance matrix sigma of t, or sorry, covariance matrix in time, sigma of t, and that evolves as delta of t plus 2 times lambda of t. So what are these two contributions to the covariance matrix? The delta of t captures the blob deformation. So sigma naught is the initial covariance matrix of the deformation tensor, And then that is just with the dot product with the deformation tensor. Sorry, that's the covariance matrix of the initial solute blob. The application of the deformation tensor to that just tells us how that blob has been stretched and rotated and compressed, etc., as the flow goes along. So delta tells us about the reversible deformation that our original solute blob has undertaken just due to the stretching and the rotation in the flow. The second term, lambda, the second contribution to the covariance matrix, contains the irreversible components due to diffusion. So D naught is the diffusion, the diffusivity in the system, and we can see that the integral of the dot products with the deformation tensor and the diffusivity gives the contribution to lambda, and that tells us how the interplay of stretching and diffusion is evolving over time. So you can imagine if our element has been stretched early and diffuses, that's a different problem to being diffused and stretched late over the history. This term lambda will take care of that. So we have two different mechanisms that essentially propagate the covariance of our Gaussian blob as it moves through the flow. So here we can see that the deformation tensor is intimately mixed with, tied up with mixing and dispersion. And as we can see from the blob dispersion, it's that deformation history over time that controls mixing. More generally, if we want to move away from just a Gaussian blob, but to more general concentration distributions, we can also take our advection diffusion equation in Lagrangian and move it from Eulerian into Lagrangian coordinates. And when we do that, we find that the advection term drops out because of the move from Eulerian to Lagrangian coordinates. But the dispersion tensor is now augmented as shown on the right here, and the deformation tensor is augmented as shown. So the deformation tensor exactly gives us the transform into the Lagrangian frame and shows us how deformation and deformation history completely governs mixing with time. So the key point is characterization of the deformation tensor is key to prediction of solute mixing and dispersion across these wide range of flows. So we need a convenient frame for being able to characterize and understand the deformation tensor. If we introduce a coordinate frame that moves and rotates with the flow, so x naught is the position of our Lagrangian tracer particle with time, then we can introduce a new coordinate frame x prime, which is equal to q, dotted with x minus x naught, and q is simply a rotation, or orthogonal rotation matrix. And if we decide on the right form of q, we can end up with what's known as a protein coordinate frame, or essentially a coordinate frame where epsilon, remember epsilon is the velocity gradient, is upper triangular, and from that the deformation tensor is also upper triangular. This gives us some really nice physical insights into the deformation tensor and allows us to develop some stochastic models for the deformation tensor from this more simplified form. If we look at the velocity gradient tensor on the top left here, the diagonal components shown in red quantify stretching of fluid elements. So epsilon 1,1, epsilon 2,2, epsilon 3,3. Turns out the one coordinate is aligned with the streamline itself in steady flows. And so that's the stretching along a streamline for a steady flow, and the 2 and 3 coordinates are then transverse to the streamline. And so all of these elements capture the stretching or compression of our fluid elements. The off-diagonal terms, so the epsilon 1,2, the epsilon 1,3, and the epsilon 2,3 are shear terms. So we can split apart stretching and shear as shown. And likewise, if we consider the deformation tensor, the diagonal components F11, F22, F33 are then exactly the amount of stretch that our solute blob has undertaken, or our material element has undertaken, and F12, F13, and F23 are the off-diagonal ones, are the shears. It also turns out that the evolution equation for the deformation tensor is much, much simpler. Those diagonal terms are just the integral or the exponential of the integral of the components of the velocity gradient tensor. And we have some fairly simple integrals for the off-diagonal terms as well. So we actually have some simple equations to propagate the system. It turns out that the Lyapunov exponents that we were talking about earlier that characterize the amount of chaotic mixing or deformation are just the ensemble averages of the diagonal terms of the velocity gradient tensor in this protein coordinate frame. And it also turns out that, as I said, for steady flows, the protein coordinates are the streamline coordinates of the flow. So the one direction is aligned with the flow direction, and the 2 and 3 are transverse. And for helicity-free flows, which I guess is an additional constraint on top of that, these protein coordinates are then the stream functions of the flow. For unsteady flows, this breaks down, this coordinate frame tumbles with the flow because you have extra degrees of freedom in the system. If we revisit our picture of fluid deformation under steady and pulsed injection, then we can see that the components, the F11, F22, and F33 diagonal components capture the stretching of these material elements along the sheet and across the sheet. And the F11, F12, and F23 are the shears associated with that as well. So we get this nice physical understanding of what's going on by using this coordinate frame. If we look across our various flow classes, it turns out that the number of non-zero diagonal and off-diagonal elements changes with the complexity of the system. So as we increase the complexity of the system, we get more non-zero independent elements in the velocity gradient tensor, and also the deformation gradient tensor. The diagonal components for the non-chaotic cases are all 1. And as we increase complexity going from 3D steady or 2D unsteady, we have 1 Lyapunov exponent in those cases. And finally, for 3D unsteady flows, we can have 2 Lyapunov exponents that are independent. So all the behavior and all the complexity of the system, these various flows from simple to complex, then manifest as just different constraints on the system. So it looks like that this velocity gradient in the protein frame captures the constraints and the complexity across all the flow classes. So how do we use this? How can we apply this to our computational or experimental data sets? If you're given a 2D or 3D steady or unsteady velocity field, the first step might be to perform particle tracking to generate our protein frame. So identify this rotation Q of T. I haven't gone into the details of how to do that, but there's a way to do that. And then from that, simply along the particle trajectories, then pull out the protein velocity gradient along many path lines and start gathering statistics. So we can look at the PDFs of the elements of the protein velocity gradient, the velocity magnitude itself, correlations between the two, decorrelation, and so on. This framework can be applied to quite complex flows. We've applied it to get the PDFs of these for, say, turbulent flows from DNS calculations from the Johns Hopkins database. And we can characterize fluid deformation and so on in these very complex unsteady flows. And likewise, as I said, it can be applied to steady flows. The characterization of the velocity gradient tensor epsilon then allows us to predict the deformation tensor through appropriate stochastic models and so on, and then we can use that to quantify solute mixing. So let's look at how this might work for steady flows. In steady flows, we can develop a random walk for the deformation tensor. This deformation CTRW, so continuous time random walk, captures the stochastic nature of the medium and preserves the underlying dynamics. For steady flows, the velocity components and the velocity gradient decorrelates with streamline distance, not time. So traditionally, people would approach this by having a decorrelation time as particles move along streamlines. However, for porous media, there is a fixed correlation structure, spatial correlation structure in the medium, so it makes sense that decorrelation happens with streamline distance, S. Once you can establish Markovianity of the system with decorrelation length, then we can set up a continuous time random walk in S space. So if we think about particles moving along the trajectory as shown on the right here, at the initial step, S0, we then move to the next step, S1, which is just given by a fixed decorrelation length, SD, and then fixed correlation length, SD again, to get to S2 and so on. So we have a random walk in S space. The time from one step to the next is just given as SD on the local velocity Vn, and therefore we can set up a random walk for the components of the deformation tensor. We can develop closed form solutions for this, and that then gives us predictions of deformation in 2D flows. And so for 2D steady Darcy flow, this is exactly what we've done, and we found various regimes of stretching, algebraic stretching for the off-diagonal components. In 2D steady flow, we only get longitudinal mixing, and so it's only the F12 component that grows with time. All the other ones just oscillate, and we can see various superlinear and sublinear stretching based on essentially details of the correlation structure of the field. So using this framework, we can develop from ab initio calculations, we can calculate the stretching rates of material elements as they move through the flow, and then that can be applied to solute mixing models. So we find that the length of material elements, L of t, grows as a power law, and that power law exponent varies between 0 and 2 based on details of the flow, which I won't go into at the moment. This lamella mixing model, or sorry, these stretching dynamics then feed directly into lamella mixing models, which give us the solute concentration PDF. So in previous work by Tanguy Leborn and co-workers, they've been able to develop models that show the evolution of the solute concentration PDF for a plume, and the inputs are given by this technique here. Note, we also don't have any transverse macro dispersion here because there's no persistent growth of the transverse components of the deformation tensor. If we think about 3D steady isotropic flow, so we move from 2D to 3D, but the conductivity field is isotropic. As we talked about earlier, these are zero helicity flows. So these flows have dual stream functions. And because of this dual stream function structure, we find that one of the components of the velocity gradient is 0 in the protean frame, and essentially the shears decouple in the system. And without going into details, this really is just two 2D flows that are imposed orthogonally to each other. So we get exactly the same type of stretching dynamics as for a steady 2D flow, and it's the constraints that are imposed by the zero helicity nature of these flows that give you this behavior. So we get exactly the same stretching dynamics. We find that these off-diagonal terms grow as a power law between 0 and 2, and we get the same dependence on the correlation structure of the flow. Again, there's zero transverse macro dispersion, and this is something that's probably not widely appreciated at the moment. So the net result is that for steady isotropic Darcy flow, we have the same kinematics as two superposed Darcy flow, and so we have the same sort of stretching dynamics or fluid deformation and similar mixing dynamics as that. And the argument would be that by using an isotropic conductivity structure, you're constraining the dynamics of the flow a lot. If we then switch to steady anisotropic Darcy flow, so now the conductivity field can be anisotropic, we get a very, very different state of affairs. These constraints associated with helicity break down. We now can see braiding of streamlines as they move through the flow. They're no longer constrained to these two-dimensional stream surfaces. We can measure Lyapunov exponents in the system, and we find that the Lyapunov exponents of the system is chaotic. The Lyapunov exponents increase with the conductivity variance of the system. And we can apply this framework to capture the deformation CTRW. And in this case, now we find the off-diagonal elements of the deformation tensor grow as a product of a power law and an exponential. The exponential is governed by the Lyapunov exponent, and the power law, we have the same dependence of t to the r, where this r parameter is dependent on the details of the correlation structure. So using this framework, we can start to understand how we get mixing in these more complex anisotropic Darcy flows. And this is essentially the building blocks then of developing models for mixing and solute mixing and so on based on this deformation. The CTRW theory for these flows agrees very, very nicely with the direct numerical calculations. So it seems like that the framework here is quite robust. Okay, so changing gears again, let's have a look at mixing in unsteady flows. And for unsteady flows, we need to extend our stochastic framework a little bit. The chief difficulty for unsteady flows is velocity has multiple forcings, and so it can decorrelate both in space and time. So for porous media, we can see decorrelation of the velocity of a particle as it moves through the flow when it moves from a high to a low permeability region. But also, if the flow is unsteady, the forcing can be fluctuating in time, and so we can have decorrelation of the velocity of a particle, even if it doesn't make any significant moves in space. So we need to develop a way of handling these two. To set up this problem, we've looked at a model Darcy flow that's being forced by pressure gradients in the orthogonal directions, leading to the steady flow of V1 of x and V2 of x shown in the top right. And then we've constructed a fairly artificial looking unsteady flow by combining those with a forcing f of t. So we multiply the V1 field by f of t and the V2 field by 1 minus f of t, so they're negatively correlated. And f of t is a random function which has a well-characterized correlation structure. If SD is the decorrelation length for those steady flows, V1 and V2 of x, and TD is the decorrelation time for the forcing function f of t, then the overall flow, or the overall velocity v of s comma t, the velocity along a path line, has a correlation function of e to the minus s on SD minus t on TD. So the overall correlation function is just simply the product of the individual correlation functions in space and time. And I've skipped over a lot of details here, but we can now show this result quite rigorously. Decorrelation occurs when a parameter r, which is defined as s on SD plus t on dt, is greater than 1. So when we cross a threshold of the magnitude of the decorrelation, whether it's due to space only or time only or a combination of space and time, once that threshold has been passed, then the system decorrelates. So this new variable r of st, when that becomes greater than 1, the system decorrelates. So the velocity process is not Markovian with respect to space, and it's not Markovian with respect to time, but it is Markovian with respect to r. So we can then develop a CTRW or a CSTRW, continuous space-time random walk, with respect to r. And the random walk is as follows. We increment r by 1 because that's the decorrelation condition. The new spatial location along a path line Sn plus 1 is the old Sn plus delta Sn, and time is incremented by delta Tn. But now delta Tn is given by Sd on Vn plus Sd on Td, so that's just a mixture of the spatial and temporal contributions, and delta Sn is the same thing multiplied by the velocity. Down the bottom, we can look at time series data for velocity along a streamline, where the first plot is with respect to time, and we're seeing clear intermittency of the velocity process when we take fixed steps in time. The second, in the middle down the bottom, is the velocity along a streamline when we take when we're sampling with respect to space, and again we can see intermittency there with respect to space clearly. But on the right, we see the velocity process along a streamline with fixed increments in the r coordinate, and it's there that we see that the system is truly Markovian. So we can see that this construction for unsteady flows gives us Markovianity which is the basis for our continuous time random walks or space-time random walks. We can now apply that to unsteady Darcy flows. So now our model flow that we looked at, where we had two velocities set up orthogonal to each other, we can set up sampling of the system. We now find that our deformation CTRW admits chaotic dynamics. So the diagonal components of the deformation tensor, one of them grows exponentially as a Lyapunov exponent, the other one decays. And the off-diagonal one grows exponentially as well with a constant prefactor. The deformation in this system, therefore, is governed by the Lyapunov exponent. We find for these flows that also increases as the log conductivity of our Darcy fields, and we get a maximum with respect to the decorrelation time for reasons that I won't get bogged into today. So at the moment, it seems like this framework is able to capture deformation in these 2D unsteady flows, which is something that's never been done before. And again, the next step here would be then to link this to solute mixing. So again, by characterizing the amount of deformation that happens in these flows, we have a basis for solute mixing. The unsteady pore scale flow is a little bit different. I might, in the interest of time, just skim over this quite quickly. For this push-pull flow, we've found this heterogeneous and anisotropic dispersion, which comes from the interplay between diffusion, irreversible diffusion, and reversible advection. When we start looking at the developing stochastic models for this, we find that we can find these manifolds as to where we get these hotspots of high intensity of diffusivity or effective diffusivity, and we also see that the anisotropy comes through from the deformation tensor here. And so when we start making plots of these fields, we find that correlates very strongly with the observed concentration fields for a model flow. So we're not looking at the experimental data here. Here we're looking at a model flow to test out these ideas. The basic result we've found, though, is this is now the connection between the observed experiment and the underlying deformation dynamics. And now I think if this movie will play, no, it won't. But essentially it gives us a way of understanding how diffusion and advection are playing together in this push-pull experiment, and ultimately being able to pull out more understanding and statistics of the processes underlying that. What this really allows us to do is then make estimates of the Lyapunov exponent from our experimental concentration fields. Here we are. Now this is playing. So for the model flow here, this is what the push-pull experiment would look like for our model flow, where we've looked at this time periodic sine flow. And now we'll be able to make a connection between the two and the underlying deformation. So that gives us a basis of understanding our experimental data here. So this is work in progress at the moment. Okay, the only other thing I really want to touch on is just heterogeneous Lagrangian topology. Earlier, we looked at these class of flows that had these different mixing regions. We had non-mixing regions, KM islands, and then surrounded by chaotic seas and so on. The complexity here is that we need to characterize the deformation in these different regions because they are quite different. So the stochastic models are great when you've got the same sort of general behavior in the background, but for these flows here, we need to apply these techniques in each subdomain because the mixing dynamics are quite different, and so a general stochastic framework won't resolve that if that's of interest. Okay, so to summarize, first of all, application to data sets. How do I predict the solute mixing and dispersion from my computational or experimental data sets? The first step, or whether you've got 2D or 3D steady or unsteady flows, is characterize the PDFs of velocity and velocity gradient. And also you need to look at the correlation structure of the velocity gradient, or of the velocity, sorry. We can use that then to solve the deformation tensor using a deformation CTRW, or in unsteady flows as a continuous space-time random walk. And that gives us the stretching rates of the various components of the deformation tensor. And that's really important because once we know the stretching of the various components of the deformation tensor, then that allows us to put these stretching rates into dispersion and mixing models for the local concentration PDF. There's a lot more work to be done in developing beyond steady 2D flow. How do we develop these dispersion and mixing models for 3D flows, for unsteady flows? That's a hot topic in fluid mechanics more generally. But that's really the next step to take this work and understand mixing. And then, of course, once that's done, you can then implement the mixing and dispersion models, for example, as subgrid scale models for solute plumes and so on, as well as understanding the underlying physics. So the conclusions and directions, really the main message today is porous media flows span from simple to complex Lagrangian kinematics, and we have rich data sets. We have a stochastic framework that resolves these kinematics, and the main story is that fluid deformation governs mixing. We have this protean frame that allows us to understand that properly and the constraints on that. Deformation across diverse flow is characterized by the velocity and the velocity gradient statistics, and the deformation CTRW gives us a first principles stochastic framework for that. The next steps is to then take these deformation rates and put them into models for solute mixing and transport. So we need high resolution data sets for velocity and velocity gradients. We need to develop the lamellar mixing models, extend beyond steady 2D flows. And I think a really interesting area is linking the medium properties to these deformation rates. I'd just like to thank some of our project sponsors and for your time. And I'm, as I said, very sorry to have a calendar malfunction today, to put it mildly. Thank you.